Okay, so welcome everybody. This is Shamik's second lecture in an indefinite series on celestial amplitudes. So Shamik, take it.
Okay, thanks. Let me start. Okay, so I'll talk about how the space-time translation actually works on the sphere. So let me just start by doing some recap. So last time we defined these conformal primaries. Okay. So denoted in this way. So ZZ bar are the coordinates on the sphere or on the plane paper. So then these were defined as Mellin transforms of the creation annihilation operator. So sigma, where this epsilon equals plus minus 1 for annihilation plus creation operators. Okay, and this H is given by C. So sigma is the spin or the helicity of the massless particle. Okay. So now, so this was the first, and then the second was that the important property was that this SL2C, which is the lower, basically the Lorentz group in in 3+1 dimension. So this acts on the celestial sphere as the group of global conformal transformation, and under this transformation, this conformal primary wave function transforms like a primary in a conformal field theory. With scaling dimensions h bar. Where this A, B, C, D, so this is a 2x2 matrix in SL2C. So main property is that the determinant of this is 1. Okay. So this transforms like a primary with a scaling dimension h bar. Okay. Now number 3 was that you can define the correlation function of these primary operators, which are essentially Mellin transforms of the S matrix. Okay, so this S, this is the S matrix element. Okay, and of course the number 4 is that this has this. So this indeed transforms like a correlation function under SL2C. This will transform like the correlation function of a CFT. So this essentially becomes where Wi is so this is the basic thing, and this correlation, so this is called sometimes called the celestial correlation function, and this is essentially the object of study. Okay, so now let me go to the.
Samita, I have a confusion.
Yeah, just yeah. Go ahead.
S matrix has this, although I can write say P1, P2, P3, P4, but there is a momentum conservation which reduces one variable.
Right.
What happens here?
Yeah. So in this case, also we'll see that there is a these S matrix which I have here. This S of epsilon. Okay. Actually, there must be a pointer somewhere. So this S matrix, so that has the delta function. Okay. So this S is like the way we write the M delta 4 P in minus P out. Okay. So then you just do this integral. Then whatever you have on the left hand side. So whatever you get as the result of integration is essentially the left hand side. But we will see that it has some. So this delta function of this piece, so that that will be translated into some things which are not usually found in conventional conformal field theories. Okay.
Okay.
Yeah.
Shamik, there's
Yeah,
a
so
pointer next to the finger, by the way. There's a pointer next to the finger. If you click that, that becomes a pointer.
Oh,
The
so
next to it.
This
Yeah.
one.
Yeah.
Okay. Right. So this one.
Yeah.
Okay. Thanks.
Yeah.
So
Shamik,
this
I
is
have
one
also a question. This is the inversion which gives you S in terms of this inverse Mellin transform explicitly known, because there are some subtleties with choice of contours and things like that.
Well, so that of course. Well, so if you just yeah, there may be some. Well, I mean, there may be things about the choice of contour, but as it stands, if you just look at this transformation, okay. So this, of course, can be inverted. Like I think, well, this S you can write as some product. Okay, so this well, the way it is done is that you. Okay, so let me just write d lambda I by I think omega I lambda I minus 1. Okay, must be some times this correlation function. So this you can do, but then the choice, yeah. So here actually I have written this delta as 1 plus I lambda. Okay. I think, well, yeah, this must be yeah. So this is the form of the A. Now you can of course choose. So this lambda integration. Now that well, so here I am just writing it on the real line, but I think you can have some other choice also. But I have not. I don't have any detailed idea of that. Like, well, I mean, it was not really required at any point. But the thing is that, yeah, so this, at least formally, this one actually exists.
Yeah, formally it exists, yes. So people have not investigated this form that you've just now written.
Yeah, so in this way it exists. So that thing is fine, and it has also been used. So I will use it not in this lecture, but in the next day. But the thing is that whether like which contour is more useful or which contour has to be used for, like if you have something specific in mind, then
no, I was going to ask you that have people examined the high energy limit of this? Things like the Frossard bound starting with this formula.
Yeah, high energy limit in this year, I think this was, well, I think Taylor et al. Actually studied this somehow corresponds to lambda going to infinity. Okay, in this language. But yeah, well, I mean, I don't have any good like detailed answer to that actually. Yeah.
Okay, thank you.
Yeah. Okay. Yeah, this is an important thing, but we'll see that. Yeah, so far. Okay, so now let me go to the space-time translation. Okay, so there are two ways of doing this thing. So first, let me do this thing. So we have these operators, conformal, primary. Okay, so now let us, so we can now the space-time translation. Generators, of course, are 4 of them. So H is the time translation. So this is the Hamiltonian. Okay, and let us consider just a, okay, and this H is commutator. So I want to see how does say the space-time how does the Hamiltonian, so it is time translation. Okay, so it acts on phi. So for that, so let us just write down this commutator. So this commutator is just, you know, that minus epsilon p0 e epsilon omega zz bar sigma. Here the p0 is omega times 1 plus zz bar. Okay, so you can write also as minus epsilon omega okay. So now we can compute this commutator between H and phi. So if you just look at this integral, so we can take the H inside the integral, okay, and then this of course becomes okay. Now, so once I substitute this, what I get is so this comes out and I have a factor of omega. So this you can write as omega to the power delta plus 1 minus 1 a epsilon omega z bar sigma. Now this integral is essentially this integral, but the delta has been shifted by 1. But since the spin does not shift, so what it essentially does is that this h and h bar, both of them shift by half. So that means I can write this object as phi epsilon h plus half, h bar plus half, and then z bar. Okay, so the commutator of the Hamiltonian with this conformal primary is given by this with the shifted weights. Okay. So similarly, you can do the same thing for the other translations like P1, P2, and P3. So those you can.
Sorry, Shamik, you made a comment that the spin does not shift. Where does that follow from?
Yeah, so this is essential. So you can see that this is just this multiplication by this omega, this scale factor, which is this epsilon omega into 1 plus z bar into a.
Okay.
So this sigma, it is not doing
Oh, I see. Sigma
anything
does not
on the
have,
spin.
okay.
Yeah.
Okay.
So this remains unchanged, and
right,
what happens is that you take it inside the integral, then this you have an so you can take 1 plus z bar outside the integral because it is just a, and then this delta shifts by 1. So now what you get is that it is the same integral, but now delta shifts by 1. So we can say that this is essentially the conformal primary with h bar, each of them shifted by half.
Thanks.
Yeah. So yeah, each of them shifted by half because the spin will not change. Spin is h minus h bar, which is the same because each of them shifts by the same amount. So similarly, one can see, for example, that this will be just given by minus epsilon z plus z bar. So these are all the 4 of them. In fact, you can simplify these things. It is more useful to, in fact, write it in a form which can be easily generalized to the super translations, which are the local version of this global space-time translation. In fact, if you look at these computators like this H and this P3, so you can basically go to the light cone basis. So it is like H Similarly, epsilon ZZ bar then you have another P1 plus minus IP2 by 2 comma this of course just given. Okay, so suppose P1 plus IP2 so that will be minus epsilon Z similarly so this light cone basis it is just useful. We'll see minus epsilon Z bar okay, so this is we just did this because it looks like that. Well, so these are basically you can see that these phi's they are multiplied by 1 Z bar Z bar. So it's like 1 Z bar and Z bar, and then with super translations, those will be generalized to this form where m and n are any integers. Okay, so those will be so that's how actually, yeah, so that's why this way of writing this thing is useful that we'll see also in the next lecture when you talk about the super translation word identities. Okay, so these are like, okay, so this is not important actually. Okay, so this is okay, so I'll do it next. Okay, so now let me talk about the different.
Can I ask a question?
Yeah.
Hello.
Yeah.
Okay. So so is there anything special about this P2 commutator?
P2. Which one?
The P2 commutator, because of this I factor. I mean, is there any physical interpretation for this exact form of this P2 commutator?
No. Yeah. So this I has to be there. You can see because it is Z minus Z bar. So it's real. So like Z minus Z bar is imaginary. So it gets multiplied by I. So that gives you the real thing.
Okay. Thanks.
Yeah. In fact, so this is essentially okay. So let me just say. So this, of course, last time I wrote down the way I wrote down the null vector in this way. This is the null momentum. So 1 minus ZZ bar. Okay, and this essentially follows from this well-known commutator. Suppose this is a creation operator, AP, sorry, AP comma sigma is just minus P mu times AP sigma. Okay, so this is essentially what I wrote down here. So
Okay, thanks
P1,
for that.
yeah, so you can just take it inside. So yeah, so this is commutator with phi, but then this is essentially this is what I wrote down. So this is like H, and then you can do P1, P2, P3. So this is, I wrote down P0. I put an epsilon. So the epsilon is the sign. Essentially, you can see it depends on whether you have A or A dagger. And then I just wrote the P0 is omega times 1 plus ZZ bar, which comes from here. Okay. Yeah. Okay, so now let me, so an alternative representation. So this representation has another important use. Okay, so that I will mention. So this is, then for more details, this. Okay, so what we do is the following thing. So we start with this primary operator. Okay, and what you can do is that you can define a Heisenberg picture operator. Like basically it's a time translation. You can define as exponential IH capital U. H is the time translation. Okay, in fact, you can, instead of this, you can also use this H plus P3 because that is more actually H plus P3 by 2. But let me just do it in this way. So you can apply this to this. So this becomes okay. And now we know that how this is transforming. So this will become exponential minus I epsilon P0, okay, U A epsilon omega ZZ bar sigma. This is a standard rule that this is how the time evolution of the creation or the annihilation operator is. And the P0 is just this omega times 1 plus ZZ bar. So what you can do is that you can define this in this way. Epsilon omega small e sigma, where I have defined this small u as essentially this capital U times 1 plus ZZ bar. Okay, so this operator, this U dependent transformation, so you can call it just the U. Okay, so this operator now depends on three coordinates U, Z, and Z bar. And the point is that you can easily check that the, so the first thing that will is that how does SL2C acts on this. Well, so far what we have done, you can use all those things to show that under SL2C transformation, this operator will transform almost in the same way. So you have the same prefactor. And then okay, the U transforms, except that now U transform in this way. Okay, so this transformation law just follows from so if you don't want to go, like, you can take it as an exercise, or if you don't want to do this, then you can look at this paper where it is done in complete detail. And the thing is that, so this essentially tells you is that basically, so this phi so it's an operator on a three-dimensional space with coordinates u, z, z bar, on which this SL2C acts geometrically, can act, on which SL2C can act. And how does this act? So this is this law. So this is one point. Now, second is that how does space-time translation work? Okay, so you can do the same thing. So you can translate this operator So suppose you do this, say e to the power IHA. Okay, then you will see that this is, you can just use the definition of this phi u z z bar, these three-dimensional fields, and then you will see that this essentially acts as you will have a times 1 plus z z bar and z. So this acts only on u, but not on z z bar. Okay, so this is the constant. This is how the Hamiltonian acts on this. So this does not note that this is not shifting the conformal dimensions h bar, but you can actually absorb that shift in this geometrical shift of this u. Okay, and z z bar does not change. Similarly, you can do the same thing with, say, P1, P2, and P3. So I'll not write them. So let me just or basically, actually, the good way to write this is that okay, you can write this as in this way: e to the power I p dot ap is the generator of the space-time translation. and A is a 4 vector, so it is basically A0, A1, A2, and A3. So this essentially becomes, so you get U plus A0, 1 plus ZZ bar. Well, depending on the sign of this here, minus A1, and then plus I A2 Z minus Z bar, and then minus A3 1 minus ZZ bar, and then you have Z comma Z bar. So again, space-time translation acts only on U but not on the ZZ bar. So U shifts. Okay, so you can see. So you can see that in the UZZ bar space, the space-time translation acts as U plus some A plus BZ plus CZ bar, or okay, C should be at least for here. I take this to be B bar and B. Okay, so this is how you can see that you can think of these three-dimensional fields as living in this space UZZ bar on which the space-time translation acts in this way. So this is essentially this transformation, but I have just redefined like this capital A is essentially A0 minus A3 and things like that. So similarly, this C is just A0 plus A3. So that is the coefficient of ZZ bar. Okay, so you just go to the light cone basis and then simplify. So that is how it acts. So you have UZZ bar, and then U shifts by A plus BZ plus B bar Z bar plus C ZZ bar, and ZZ bar will not change. Okay, so to sum up, we can see that these fields, so these three-dimensional fields live in the UZZ bar space on which point array group acts as, so the first is the Lorentz transformation or SL2. And then how does the space-time translation acts? This is how. Now it turns out that this is essentially the way. So now if you go back to the okay, so let me now go back to the last talk where we talked about, you can see this sphere, okay, and then we wrote down, so this is a Minkowski space, so this is a Penrose diagram of the Minkowski space. So here I have written down the metric, and then we went to this coordinates is r, theta, and phi, and then I have the retarded time u. So in terms of this, so this ds square had this form, and then we showed that at r, as r goes to infinity at fixed u, theta, and phi, the induced metric is degenerate because it's a null because chi plus, so that's a null hypersurface, and it has three coordinates u, theta, and phi. Okay, so these are the coordinates. So the coordinates of the, say, the future null infinity is just u, theta, and phi. Okay, and now what one can actually show, I mean, it is actually, well, I mean, it is just a, well, I mean, it is a simple algebra. What you can show is that if you just look at the Poincare transformations in this r, theta, phi, and u. So this u, r, theta, phi coordinates, and then if you take this r going to infinity at fixed u, theta, phi, say, then you will see that the Poincare group acts on this space, this three-dimensional space u, theta, phi, exactly in this way. So this transformation, so this is precisely how Poincare acts on future null infinity scribe plus. Okay, so that is the important point actually. So that means, so this means that these fields, these three dimension, they live on null infinity. And in this sense, and you can, the way we did it here, we saw that this null infinity is basically, the important point is that you get this null infinity is obtained from quantum mechanics, from relativistic quantum mechanics, basically. I mean, nothing else. Without any reference to the bulk space-time. Okay, so now what is the usefulness of these fields? So these fields are actually very useful. So what we will do is that you can basically now define these correlation functions of these fields. So it is just a small modification.
Shamik, I'm a little confused. This null infinity that you're talking about now is a null infinity in momentum space. It's not in real space.
No, but the thing is that now it has basically transmuted into the real space. So you can see from these transformation laws that the SL2C and the space-time translation, so they are actually acting on this UZZ bar in exactly the same way as the Poincare group will act on scribe class. And yes, we start with the P space, but then at the end of the day, we basically end up with the scribe class, which is a part of the real space.
So this is like saying that for each configuration in momentum space, there is a point on null infinity in real space.
Yes. Yes, that is exactly the statement.
Okay.
And it is more powerful because you can see that the Poincare group, it is acting on them in exactly the same way. Because that has if you don't have that, then of course the identification with the real space-time is not clear. So these two transformation laws, so they are actually crucial.
I see.
So along the line what Anindya was asking, that,
yeah.
So if I send out from infinity particle, they are located somewhere and they scatter and they reach somewhere in your. So I can understand that the momentum will find out the trajectory. Given the moment I find out the trajectory,
Right.
but what I'm not getting is that I feel like you just introduced by hand, right? Somewhere, not apart from the momentum space.
Yeah, so this U is, well, it's not exactly introduced by hand because this is essentially what you get if you translate this phi z bar in time. Okay.
No, I understand, but I'm saying from the scattering matrix point of view. Suppose I want to come.
Yeah, so the scattering matrix does not have that coordinate, that extra thing, the U which you have, which I have defined here. But the thing is that this is basically what. Yeah, so I will talk more about it. So what we have done is basically we have so just 1 second. So let me just so what we have done is that we have defined free theory on, okay. So this is the transformation law. And what we have done is that basically we have defined free theory on Scri plus starting from creation annihilation operator. Okay. Now you can also define a free theory on the space-time, which is of course you do by defining these fields, right? You have some dp, a dagger p, ap. I mean, okay, you have this e to the power ip dot x plus ip dot x. So what I have shown is that given ap, the a and a dagger, what you can do is that you can define two kinds of free theories, one of which is defined in the 4-dimensional space-time, the bulk, and the other one is defined on the scribes. So is it clear?
I see. And for that, do I need to come through this momentum space approach, asymmetric approach? I could have just defined this.
No. So I have not really introduced any. So this only requires the a dagger.
This requires a dagger, right?
Yeah. So you just need a set of free objects. So that's what you need. Okay.
I see.
So basically, all the ingredients are essentially these. So AP prime, like these commutators, 0, similarly AP.
Also, will there be an interpretation like earlier that the H matrix is mapped to correlation function in this way as well?
Yeah, just yeah. So that is this object which I have here. Okay, so this is a correlation function in the interacting theory, you can say, on scribe plus. Okay.
And without the U, it was a correlation function
on the sphere, right?
And so, and why do you call it an interacting theory? Other theory was not interacting. I'm sorry.
Oh, so if I just look at if I just do it all these things with a dagger and all these things, then you don't really have, well, you don't have any S. But once you have S, so that non-trivial S matrix, so that means the bulk theory is interacting. So well, I mean in that sense, probably the bounded theory in some sense is interacting. Yeah, so that's what I mean. Now the thing is that, so that is essentially the point. So I think it is, I'll just emphasize it once more. So you start with this creation and you start basically. So you start with this creation annihilation operators for the massless particles. Now the masslessness is extremely important here. Okay, so then you construct a free theory in the Fock space. Okay, so you have the vacuum, okay, and then you have the states, okay, and then all the a vacuum is 0. Okay, now if I start with this AP dagger, then I can define a space-time field, which is phi x mu. Okay, and that of course we do this integral transformation and all these things. Some you have AP. And this is your bulk field. Okay, and now what I have done is that you can also define a field which turns out to be living on the scribe class. And then I have epsilon, sorry. So this object, so this, well, so now of course the question is like, what is the relation between these two? But these two, it's not very yet. But the thing is that this is the usual Fourier transform. So that gives you, if you start with AP dagger, and if you do the Fourier transform, then you get fields on space-time. And if you do Mellin transform in this way, then you get fields on scribe class. Okay, so that's essentially what we did here. Okay, so now well, but the thing is that this of course looks quite abstract, but what is the use of this actually? Now it turns out, so let's go back to these correlation functions on the sphere. So you can just from that you can see that you have obtained this scribe class just quantum mechanically in that sense. So we have we did not really require any kind of space-time, except because we don't need that. We start with the Fock space defined in the standard way, and that I can define without reference to space-time, but then you can do all these transformations and go back to the scribe class. Okay, so now this transformation which we have here, which does not involve these coordinates and this SS matrix. Okay, now suppose if you take S, now take S to be some graviton scattering matrix in GR. Okay, now because of the bad ultraviolet behavior of the GR, which you all know about, so this integral does not actually exist. Okay, now take S to be some graviton scattering matrix in GR, then the LHS does not exist in this transformation. Okay, that you can see. Well, so there is a way of defining this thing, but maybe I can talk about some other way. But the most straightforward way of doing this, but it turns out that these three-dimensional correlation functions which involve these phase factors suppose SGR I ZI bar, and since it is GR, so sigma I will be plus minus 2. Okay, now this actually exists. So this is the use of this actually. In fact, the point is that we will use this in all practical applications like that I will do actually in the next lecture. What I will do is that I will essentially use this one, and this prefect this exponential factor which you have here, that essentially shapes the day. Okay, and that is what so it seems that to start with, these three-dimensional objects are much more well defined in GR. Okay, so that is one usefulness of this picture. Okay, but you can do it completely algebraically. Okay, so you can basically suppose you want to think about it in a purely algebraic way. Okay, so think of U as a UV regulator. In GR, okay, which preserves all the symmetries of the theory. Okay, so this is another point of view which you can take. So you can just introduce the U if you are interested in doing all these things in GR. I mean, which I will do actually at some point. I will be talking about the HV amplitudes. So in that case, you can think about the U as some ultraviolet regulator, and the good thing about it is that it preserves all the symmetries of the theory. Like all the symmetries means all the global plus local, which I will talk about in the next lecture. The local ones, which are which are like also which also plays an important, like, well, I mean, it is essentially the central object in what I do. Okay. Yeah, so this is one picture which I will actually use when I do the GR. Okay, so I will do it. So in that calculation, I will do it more from the algebraic point of view. I mean, I'll just think of this as an UV regulator. Okay, so you can do all the calculation in the three-dimensional theory, and then you can, at the end of the day, you can see that when you compute the OPE and all these things, those things, they are no longer ultraviolet divergent, and then you can come back to the sphere, which depends only on Z and Z bar, because you can see that if you set U equal to 0, then of course this transformation gives you the old one. Okay, so that is one. Yeah, so I can stop here. Yeah, I think this is a good point to stop actually. Yeah.
Shamik, one couple of questions. So
yeah,
one thing is that
please.
in the free theory, say in the four-dimensional language, when we define asymptotic states,
Yeah.
we need to take t going to infinity, plus or minus infinity. So is that the same thing as taking your capital U to infinity?
Well, so in this theory, okay, so this is of course to start with, like you just start with a dagger and you construct the free Fock space. Okay. So there, and from there you can construct something on Scri plus. Okay. So this and that of course, yeah. So that is a free theory, but it is not exactly an going to infinity of that actually. Yeah. Because
so how do we define these asymptotic states in the language of these three-dimensional fields?
Well, that so they themselves are like the asymptotic states actually.
I see.
Yeah, because the point is that if you start with, like, say, A in dagger or A out dagger, then you can construct these fields.
Yeah, but I'm not seeing where this t going to infinity plus minus infinity that we do say following.
No, but in this case, I have not actually used that thing, because what I have done is that I have just start with this this A P sigma and A dagger P sigma, okay, and then I have constructed the Fock space.
Yes.
Okay, so that is the free here. So that, yeah, so that is the Fock space. So you have the vacuum, then you create states by acting with these A daggers, and then A acting on the vacuum is C. So that's all I have actually. And also I have these objects, and that's all I need to define the fields on space-time and on Scri class.
But is this U not defined as T minus R still?
Yeah, but the thing is that I don't need that, right?
No, but
because
if Aninda's question I want to answer, then I
no. Wait. So this U. So let me just. So that's why I said that I don't need to refer to the bulk space-time, but at the end of the day, you can actually identify these two. So let me just just a minute. Let me. I have written this thing. So these are just Heisenberg picture fields. So so you can look at this transformation. So these, of course, these you can, so let me just so let me use a different notation. Okay. Suppose I write some U H times A. So no U. So it is just a name, right? So once I have the H, once I have the A dagger, I can define my H. So this is just D3P A dagger A.
I see.
Okay, and then I define this e to the power IHA 5 times e to the power minus IHA, and this is just the Heisenberg picture thing. Right. Okay, and then actually you do all these things. Okay, and then you see that, okay, now I can try to see that how does the SL2C acts on these fields.
Right. No, I got your point. Yes. Okay.
Yeah. So now actually I am not really talking about any kind of asymmetric. So I start with the A dagger and build a free, like the Fock space from there, and I have my H, I have my T's. They are just constructed like so this basically these momentum operators. So they are just these objects I construct, and that's all I need actually. And then, so now I don't need to talk about the asymmetries. I am just working completely with the free theory. And now, so I can do two things. So what I can do is that I can define the usual this transformation which gives me these fields on space-time. But then we see that this I can also define this transformation which gives me fields on Scri class. So that's all I showed actually. Mm-hmm. So I have not so far talked about any kind of interaction audio, but those I will talk about in the next lecture. So there, of course, all these soft theorems and all these things will come. Okay.
So another question was that in the final when you were defining the correlation function as the integral transform of GRS matrix.
Right. So this is in particular
the previous formula. Yeah. So the previous formula on the previous.
So
page.
This one, right?
No, the one that you wrote in the previous page, which you actually said that it is it does not exist. So I just wanted to clarify. So suppose I want.
Oh, so this one. So
yeah.
This is that. Yeah. So let me just here. So let me write it on GR. Suppose I want to do this thing, then it turns out that because of the bad ultraviolet behavior, which you all know, So this integral is not really well defined.
So suppose I took the tree level S matrix, that the integral does not exist as for that as well.
Yeah, right. So
Even
that's what
level
I
it does
do
not
actually.
exist. I see.
Yeah.
I see.
Yes, that is exactly correct. So these actually exist for gluons, but not for the gravitons actually.
Oh, why is that?
Well, that is because of the UV behavior. I mean, GR has ultraviolet. I mean, the ultraviolet behavior of GR is bad. I mean,
Okay.
Yeah, I mean, that is a standard law.
And this in the second, in the next page, when you say that this exists, it's because of this. This actually plays the role of a damping factor. So in the sense of
So this exponential factor, so this actually acts as a damping factor.
The damping factor of this in the sense of the Riemann-Lebesgue integral, where
you can basically you can do it in that way, or since the point is that since you basically complexify all the thing, so you can make the use complex, and then you can choose some use for which this will. Yeah, you can actually easily analytically continue these things in U, because the point is that so you don't have any U bar, so so it is just a holomorphic function of U's. Yeah. So in that sense, actually, you can basically shift like UI to some UI plus epsilon I delta I, and then that will be I think it is minus I. Yeah, that is actually it. Or basically you can easily analytically continue. So this delta I's are all going to 0 plus.
So is it possible to somehow smoothly see that if you took pretended that you're doing the calculation in the bulk, and then you smoothly took the calculation to say to stripe plus, then then this integral exists only then there at stripe plus and not somewhere inside?
No, what do you mean by do the calculation in the bulk? Because the S matrix, of course, it's a function. Well, it's not really. Yeah, I mean, it's not a function in the bulk. Right?
I mean, I guess I'm thinking in terms of some kind of an extrapolate dictionary that you have in ADS-CFT.
Okay, yeah, okay.
And then we can pretend that we are on a finite cutoff, and then I wanted to see that this the final equation that you make that you said only makes sense at stripe plus when you take the cutoff to infinity.
Yeah, actually, that is so. That kind of thing is not very like it's not well understood in this context actually. And the second thing is that if I make the cutoff, like if I make a cutoff in the space but that would be like an infrared cutoff, right? Whereas this one seems to be related to the ultraviolet, because I am integrating over the energy. Yeah. I mean, maybe. Yeah, I don't really know actually.
Okay.
Yeah, because the point is that the S matrix, if I just talk about the S matrix, it is not. Yeah, I should say that I don't know actually. I mean, we can talk about this. So
I was just thinking that one of the main messages that comes across all this is that you can only define scattering amplitudes in I mean, in the sense that you have boundary observables. So all the observables should be somehow pushed to the boundary. So I'm just wondering, in that language, is there a way to understand this formula?
Yes. So this is, of course, the S matrix. Of course, is a boundary observable in that sense, because you can just think of them as functions on the sphere, on the say, facial sphere.
Yeah, but to identify the boundary, I also require a coordinate which enables me to move inside.
Yeah, but the point is that, yeah, boundary in the sense that, well, you can think of that as a boundary.
Sorry, I have lost Shamik. Is it just me or Parthiv? Can you hear me?